This screencast is for Elementary Ed 4300 Methods in Teaching Science. Chapter 8, Nuclear Physics. Nuclear energy comes from the conversion of mass. Some questions that we're going to discuss in class and that are important in this chapter are: why are nuclear physicists most interested in the nuclei of atoms? And how do nuclear physicists create hydrogen bombs? These are some activities we'll be doing in class. Some major concepts. Whereas the electrons control chemical bonding, the nucleus is responsible for nuclear energy and radioactivity. We've discussed earlier about chemical bonding. This chapter is about nuclear reactions and radioactivity. The nuclei in most atoms are stable, but others disintegrate and send out energetic particles that we call radioactive or radiation. Fission is the reaction of splitting the nucleus. Fusion is the reaction of coming together of the nucleus. When the sum of the masses of the fragments is less than the mass of the original nucleus, the fusion releases nuclear energy. The fission releases nuclear energy. Nuclei that spontaneously disintegrates are said to be radioactive. Any given collection of radioactive nuclei behaves in roughly the same way as another, with individual nuclei decaying at different times. The overall rate of decay is called the half-life, which is the time it takes for half of the nuclei in a given sample of a particle element to decay. Carbon-14 is used for dating particular items found at either archaeological sites or rocks to date their age. Carbon dating is used to age particular items based on the half-life of carbon-14, which is 5,730 years. So if you were to find a particular item that was that had half of its carbon-14, you could age it at about 5,730 years. Nuclear reactions are also used for medicine. Nuclear medicine physicists and engineers are experts in the interactions between ionizing radiation and matter. Nuclear imaging, instrumentation, and radiation doses. They typically also have expertise in image processing and computer science. So, to summarize this, nuclear medicine is actually an interaction between medicine, imaging, engineering, and computer science. If you have visited an oncologist, you'll probably realize the use of imaging and radiation doses are really an exact science right now. So they use computers and radioactive materials to diagnose different problems in the human body. Nuclear medicine physicists and engineers have advanced degrees in physics, medical physics, biophysics, computer engineering, electrical engineering, or biomedical engineering. Chapter 9 is the fundamental structure of matter. All matter is really made of quarks and leptons. In this chapter we talked about how physicists now are starting to study material and matter even smaller than the nucleus. So the frontier of physics has shifted from the study of the nucleus or nuclei to the study of particles found inside the nuclei. Starting in 1930, physicists studied cosmic rays. These high-speed particles, mainly protons, are produced when in stars and rain down, they're produced in stars and rain down constantly on Earth. When cosmic rays hit a nuclei, two things can happen. First, they break the nuclei apart, spewing particles out. Or second, some kinetic energy of a cosmic ray can be converted into mass, creating new particles. Physicists picture all forces between elementary particles as being mediated by the exchange of gauge particles. Now, these particles are broken down into just 4 different forces. They operate in nature. These 4 forces include gravity, electromagnetism, strong nuclear, which holds nuclei together, and weak nuclear interactions. Accelerators help physicists study the structure of matter. These accelerators get the atoms traveling at such a speed that they can collide their nuclei, and then physicists can study the spray of the particles. The theory in which quarks are seen as tiny objects corresponding to different modes of vibrations is called the string theory, and this is one of the frontier studies of physicists currently today.